In these last few mini lectures of the semester, we are going to cover nuclear physics. In the late 1800s, French physicist Henri Becquerel found that a uranium-rich material called pitchblende emitted radiation without any energy input. This was really bizarre at the time, and as a result of discovering this, he discovered radioactivity. And here's Henry Becquerel. He's got a pretty cool beard here. This radioactive emission results when the nucleus of an atom spontaneously decays, emitting radiation or transforming into another particle. It does this because it's in an unstable state and it wants to become more stable. There are three primary types of decay processes. We call the alpha, beta, and gamma decay processes, but we'll learn more about those in a minute. I'm sure that you are already familiar with the structure of the nucleus, but we're going to give some more units here and some more, quantify these a little bit more. The nucleus of an atom is made of two different, what we call nucleons, protons and neutrons. Neutrons are neutral, they have zero charge, and they are just slightly heavier than protons. So when we think about the mass of a proton compared to a neutron, the mass of a proton is 1,836 times the mass of an electron. The mass of a neutron is 1,839 times the mass of an electron. Now, kilograms are really large units for these tiny things, the mass of these nucleons. So we use the atomic mass unit, represented as little u, to represent these small masses. The atomic mass unit U is defined as 1/12 the mass of a neutral carbon-12 atom. One atomic mass unit is equal to 1.6605 times 10 to the minus 27 kilograms. Now, we can also define these masses in terms of electron volts per the speed of light squared. Electron volts or mega electron volts over c squared. Energy is equal to mass times the speed of light. So if you rearrange that, this is Einstein's equation, E is equal to mc squared. If you rearrange this for mass, you can relate the mass to the energy and the speed of light. So mass can be the energy over c squared. So the atomic mass unit is also 931.5 mega electron volts over c squared. And here's a table which you can also find in your textbook, which shows the masses of protons, neutrons, and electrons in kilograms, atomic mass units, and mega electron volts over c squared. We use a particular notation to denote nuclides. A nuclide is a specific combination of protons and neutrons, and we're going to use this particular notation for our physics course. X, big X here, is the symbol, shouldn't say particle, it's the symbol of our atom that we're thinking about. Z is the number of protons here of our nuclide. This determines what the element is as well as its chemical properties. N here is the number of neutrons of our nuclide. And this number, or the number up here that we represent as A, is the total number of nucleons. It's going to be your number of protons plus your number of neutrons. So here, for example, we have uranium. This particular nuclide of uranium is going to have then 146 neutrons. It's got 92 protons. Then this number here, 238, the total number of nucleons, that's going to be our number of protons plus our number of neutrons. If you were to pull apart a nucleus into individual protons and neutrons, you would have to do work. You would have to overcome what we call the strong nuclear force, which tries to hold together the nucleon. This work that you have to do represents what we call the binding energy of the nucleus. You can also think of the binding energy as the amount of energy that must be added to break apart the nucleus. Nuclei are less massive than the sum of their parts because of the work that goes into assembling them. So if you just look at the mass of the nuclei of an atom, that's going to be smaller than if you tried to add together the masses of all the individual neutrons and protons that make up the nucleus. That's because of the work, again, that goes into assembling them, which is the binding energy. How do you find the binding energy of a nuclide? Well, you do it this way. The binding energy is equal to, I'm going to call this delta M times C squared. Delta M is the difference between the sum of all the constituent bits that go into your nuclide minus the actual um, atomic mass of the nuclide. Remember, there's an offset between the sum of all the parts and the actual atomic mass of the nuclide, and that difference is the binding energy. So that's the energy essentially that goes into assembling all the bits. So you'll get the mass of your nuclide, which is this quantity right here. You'll get it from a table or an appendix in our textbook. And then this front quantity here is going to be the sum of all of the masses of all the neutrons in your nuclide. So N is your number of neutrons times the mass of a neutron. And then we're going to add it to Z. Z is your number of protons times the mass of one hydrogen atom. Why do we use the hydrogen atom here for the mass of the hydrogen atom? The mass of the hydrogen atom takes into account that protons are paired with electrons, and one hydrogen atom has one proton and no neutrons. So we can sum up all of the, essentially this term right here gives us the sum of all the electrons and all the protons that are going to be in a nuclide, and then we're going to add it to the sum of the masses of all the neutrons that are in the nuclide, and then we're going to subtract it from the actual mass of that nuclide, give us our binding energy. Of course, we multiply it by C squared. I think we'll get a better understanding of this binding energy if we actually just tackle a problem. Here we're going to calculate the binding energy of the deuteron. The nucleus of the deuterium atom consists of one proton and one neutron. So it's hydrogen, but it's got a neutron. We're going to calculate the deuteron's binding energy in mega electron volts, given that its atomic mass, the mass of the nucleus plus an electron, is 2.014102 atomic mass units. And we could also find this mass of the deuterium atom in our Appendix A in your textbook. So our binding energy was this quantity that we call delta M C squared. And so we take Z, our number of protons, which in this case is 1, times the mass of one hydrogen atom. The mass of one hydrogen atom from Appendix A is 1.007825 atomic mass units, plus our number of neutrons, which is 1, times the mass of a neutron, 1.008665 atomic mass units, minus the mass of our particular nuclide. In this case, we have deuterium, and that mass is 2.014102 atomic mass units. So the binding energy, we just sum all of these pieces here. We sum up the mass of one hydrogen atom plus the mass of one neutron minus the mass of our deuterium atom, all times C squared. So our binding energy is 0.002388 atomic mass units times C squared. But we saw earlier that we could write one atomic mass unit as 931.5 mega electron volts per C over C squared. So our binding energy is 0.002388 atomic mass units c squared. And then I'm going to multiply it by this conversion factor here. In 1 atomic mass unit, I have 931.5 mega electron volts over c squared. We cancel the c squareds, we cancel our atomic mass unit, and then that just leaves us with units of mega electron volts. So our binding energy of this deuterium atom is 2.224 mega electron volt. The strong nuclear force is an attractive force that acts between protons and neutrons in the nucleus. This force overcomes the repulsive force between protons, but it only acts over small distances. So, we've talked about the electrostatic force. There's going to be an electrostatic force, our Coulomb's law equation. For the protons are going to want to repel each other. The Coulomb's law acts over longer distances. The strong nuclear force only acts over short distances on the size of a nucleus. Larger atoms with atomic numbers greater than about 30 require more neutrons to overcome the electromagnetic force that wants to repel the atoms. So here we have a graph that shows the number of neutrons versus the number of protons. And when the number of neutrons equals the number of protons, that would be this red dotted line here. But we only have stable nuclei over a very small range where the number of neutrons equals the number of protons. And when you start to get to larger and larger atoms, you have to start adding on more neutrons compared to the protons in order to keep that nuclei stable. Now, what happens when nuclei become unstable? Unstable nuclei undergo radioactive decay. They can decay in 3 different ways. They can decay into alpha particles. Alpha particles are bare helium nuclei. The nucleus of a helium is going to have 2 protons. It's going to have two neutrons. Our unstable nuclei can decay into beta particles, which are energetic electrons, or into gamma rays, which are energetic photons. There's a distance over which these particles, the result of the decay, can travel. Alpha particles don't travel very far. They can be stopped by a sheet of paper or a few centimeters of air or the fraction of a millimeter of human tissue. Beta particles can be stopped by thin aluminum plates or a few centimeters of biological tissue. And gamma rays can travel the farthest, and they travel through several centimeters of lead or meters of concrete before they get stopped in their tracks. And here is an apparatus which shows, here we have a lead box, which inside there is a radioactive source. And here we have a magnetic field. Our radioactive source is undergoing radioactive decay, and it's emitting alpha, beta, and gamma particles. And those particles are traveling through the magnetic field, and then they're going to arrive at a photo screen. And we see that the beta and the alpha particles are both deflected as they travel through the magnetic field. If they get deflected with traveling through the magnetic field, based on what we learned previously about the Lorentz force, we can determine whether or not these particles are positively charged or negatively charged. And based on how these particles deflect, you could determine that alpha particles are positive, beta particles are negative, and gamma rays go through the magnetic field and are undeflected. And so that means that they are neutral. But we know that photons have no charge. So the gamma ray traveling through the magnetic field and not being deflected makes sense. We're going to talk a little bit more individually about the alpha, beta, and gamma decay processes. Alpha decay occurs when the nucleus ejects an alpha particle, which is a helium nucleus with 2 protons and 2 neutrons. This reduces the charge of the nucleus by 2, moving the atom 2 places down also on the periodic table. And it also reduces the total number of nucleons by 4. Now, when we talk about alpha decay, we talk about the parent particle, and then it decays into the daughter particle, which is our particle that's 2 places down on the periodic table, plus our alpha particle, which is our helium nucleus with 2 protons and 2 neutrons. So if we're going to have a nuclide that undergoes alpha decay, A remembers our total number of nucleons, neutrons plus protons, and Z is our total number of protons, N is our total number of neutrons. The daughter particle is going to be this particle right here. It's going to have 4 less nucleons, 2 less protons, 2 less neutrons. In the process of this decay, you also get your alpha particle, your bare helium nucleus, 2 neutrons, 2 protons. In our problem here, we have radium, a radium nucleus that is going to undergo alpha decay into radon. We're going to calculate the amount of energy released in this decay. So we've got the mass of our radium nuclide here, the mass of our radon nuclide, and then the mass of our alpha particle. This decay follows along this process here. We've got our radium atom, and then it's going to undergo alpha decay, and when it does that, it's going to lose 4 of its nucleons, 2 neutrons, 2 protons. So we go from 226 for our total number of nucleons to 224. We reduce it by 4. Our total number of protons is reduced by 2. We also reduce our total number of neutrons by 2. And then we also emit an alpha particle, our bare helium nucleus. So the energy released in this process is going to equal the difference in mass of this right-hand side of our equation minus the left-hand side of this equation times c squared. That's our delta M here. It's the difference in mass between our parent particle and our daughter particle plus the alpha particle. So delta M, the loss of mass during the decay from the parent to the daughter and the alpha particle. That will equal the mass of our parent minus mass of daughter plus mass of the alpha particle. And so then we'll just take our quantities from up here for the mass of radium, radon, and our alpha particle, all of which I gathered from appendix in our textbook, Appendix A. And I performed this mathematical operation, and I find that delta M, this loss of mass during my decay process, is 0.00526 atomic mass units. So my energy released in this process will equal this change in mass times c squared. And I'm going to go ahead and multiply it by this conversion factor that takes me from the atomic mass units to units of mega electron volts over c squared. And the c squareds are going to cancel, my atomic mass units are going to cancel, and it leaves me with the energy released in this alpha process in mega electron volts. So I'll take 0.00529 times 931.5, and that gives me the energy released in units of mega electron volts. So remember, electron volts are 1 unit that we could use to represent energy. Beta decay occurs when the nucleus ejects a beta particle, which is an electron, as well as an antineutrino. An antineutrino is the antimatter equivalent of a neutrino. In this process, a neutron also becomes a proton in the beta decay process. So we start with our nuclide, and then we undergo beta decay. So one of our neutrons becomes a proton, which means that our total number of nucleons remains the same. A remains the same here, but we add a proton, but we lose a neutron from our created daughter particle. With the decay to the daughter particle, we also have a beta particle, which in this case is an electron, plus our antineutrino. The neutrinos are often represented with the Greek letter nu, which is here kind of a fancy V, and the bar over it indicates that it is an antineutrino, the antimatter equivalent of a neutrino. A neutrino just means like a small little neutral particle. And then we also have gamma decay. So in the final type of decay here, gamma decay, an excited nucleus emits a gamma ray, much like an excited atom emits a photon as an electron drops into a lower energy state. These excited nuclei are often the result of other decay processes, as illustrated here. So here we have a beta decay process, but our daughter particle right here is also undergoing gamma decay. So it is going to decay and emit gamma particles or photons in the process. So when you undergo gamma decay, you don't change your total number of nucleons, you don't change your number of protons or neutrons, but you do emit light.